All right, I will. I will begin. Ahem. Ahem. Dear Father, we thank you for this time we have to meet together to study your creation. Again, I thank you for these students. Just ask you to bless our work today and just help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. So, I think I owe you guys an example on continuous mass distribution. So let's talk about center of mass. For continuous distribution. So, example 1, suppose you've got a, you got this stretch of wire, and it's a peculiar wire, all right? It's constructed in such a way that the density, the mass per unit length, all right, varies with position. So I'm gonna construct this wire. I'm gonna imagine that the density lambda, which is the mass per unit length dm dx, all right, I'm gonna let it be equal to some constant alpha times x, all right. So what this means, and we're going to say that this is x equals to 0 here. We're going to say that this is, over here, x equals to L. So you've got this, like, ruler or something, some object, and the density of it starts, it's very, very small to start with at 0, and then it gradually increases up to its largest value at the end point, right? So in this situation, there's more mass towards x equals to L than there is at the origin at x equals to 0, right? A question then we can ask is, given this distribution of mass, all right, where's the balance point? Like, where is the center of mass in this situation, right? That's a question you can ask. Now, we talked about center of mass for a finite number of particles last time in 3 dimensions. Now I'm just kind of asking a more complicated one-dimensional question to start class. So there's a few different things we need to do here in order to solve this problem. One of the things we need to do is to figure out the total mass of the rod. How would I figure that out? How would you figure out the mass? What's the total mass in this case? It would be the integral of dm, right? Over the rod. How would you actually calculate that? I mean, this is a lovely sentiment, but what does it mean? To me, that's just a guiding principle. To find m, you add up the little dm's, right? dm's. So, man, who's scratching my board? Dude, it's not cool. It's cost me like $20 at Home Depot. I mean, it cost somebody $20 at Home Depot, whichever vandal installed this in the weekend. But 0 to L, I integrate from 0 to L what? See this? This means what? dm is what? Alpha x dx, right? So I have to integrate alpha x dx. That's my dm. Alpha is a constant, right? It's easy enough to do. You got alpha over 2, x squared, evaluated from 0 to L. So the answer for the mass is it's 1/2, alpha over 2, L squared, right? So this is the mass of the rod. Right? What is the formula for center of mass in one dimension? Center of mass in one dimension, how's that go? We have x bar, which is equal to what? It's 1 over m, and then the sum, I equals 1 to n of m sub I times x sub I, right? This is the formula for center of mass in one dimension. It's the weighted sum of the x coordinates of the masses that are strung out along, let's say, the x coordinate axis. So how should I figure out the center of mass in this situation? What do I need to do? this is calculus-based physics, right? This is calculus-based physics, and this is one of those places where we're going to use calculus. How should we do it? I need to like come up with an elaborate pulley system so I can just like pull a rope at the front of the classroom to like shut these doors, you know? Or I could just like learn how to use the force, I guess, if you believe in that sort of thing. I guess I really don't. Although one of my absolute favorite moments in my junior level classical mechanics class, I don't think I've told you guys this yet, is like we were right in the middle of discussing Newton's laws and everything and talking about the force, and the professor asked where the force was. And this one grad student just whipped up his hand. He's like, "But professor, the force, it's everywhere." It was amazing. Like he delivered it so well. Like we were laughing for like 3 minutes. It totally ruined his lecture. It was brilliant. Anyway, so my point here is that if this is how you do it for a finite number of masses, right? In the case that you have a continuous distribution of mass, this gets replaced with 1 over the mass times the integral of x dm. That's how you interpret this. The finite sum in the limit becomes a continuous sum, which we call the integral. And so here, how does that work out? The center of mass coordinate x bar here would be 1 over the total mass. Well, we already calculated that. I'll leave it like this, right? And we're supposed to integrate from 0 to L of what? dm. What is dm here? Well, dm is alpha x dx, right? So this gets you a x times alpha x dx. All right? And so how's that go? Looks like we got ourselves a alpha over m. And that's an x times x, which is x squared. X squared integrates to x cubed over 3. You long for simpler times with integrals like that, right? You're in calculus 2, you're like, please, someone ask me to integrate x squared, right? Like in calculus 1 at the end, you're like, I think I got it. Now you're like, why can't we do that? No, it's got to be the arctangent or whatever, right? But so that's alpha over m, and this is L cubed over 3. Right? And so there you go. That's the center of mass. Now, that's a dumb way to leave the answer, right? We don't want to leave the answer like that. Where is the center of mass? We'd like to state it in terms of L, right? So what is this? What is M? Right here, right? So we've got, let me write it out here. We've got alpha L cubed over 3 times M, which is 3 times alpha L squared over 2, right? How does this simplify? The alpha doesn't matter, right? The alpha doesn't matter at all. That whatever that constant is, it cancels, right? And looks like we get what? 2/3? 2/3 L. I believe. So the center of mass is right about here. Two-thirds of the way over. Now, my pictures, how would you actually achieve this kind of linear density anyway? My picture's kind of dumb. Like, can you guys tell me, how could you actually achieve such a thing in principle? Some of your mechanical engineers or whatever, future mechanical engineers. Yeah. Heat treated different ways. I was looking for a less, here, how about this? If I make this shape, right? So that, and then I look at this shape, right? I could treat this shape as if it were a line where the density is increasing, right? So it would have density 0 here, if you just think of this as a line, right? And then it would increase linearly up to its largest amount. So you could think about it, this for example, could be like the density of like a triangular wedge, like a wire that's, you know, an arrowhead, if you will, a kind of very boring two-dimensional arrowhead. But if you had this shape, right? If you had this shape, we could essentially figure out that the center of mass of that shape is where? Two-thirds the way over. That's where it is, right? Because I think you can argue that the mass at each, if you you could basically chop this up into slices like this, and find the dm for each one of these. It would be proportional to how far you are over, linearly so, and it would be the same mathematics. You could do that. And then the symmetry of the problem suggests that the center of mass has to be where? On this line, right? So you could kind of think of it one-dimensionally. Yes, sir?
So density equals d in dx. What does d in dx mean there?
Mass per unit length. So this is so-called linear mass density. There is also, in principle, you could talk about, this is typical notation, sigma is oftentimes like dMdA. This would be area mass density. Or you could talk about rho, which is dmdV. That would be, volume mass density. And if you wanted to calculate the total mass for, say, so for area mass density, we'd be talking about something like a laminate, something that's essentially like a two-dimensional object where you can talk about the mass per unit area. You did integral over the area of the area density, find the total mass. If you had the volume density, you'd actually have to integrate, like this. dV, dm would be rho dV in that case. And so like to find the total mass, you integrate over the volume of rho dV, right? You'd be like, as much as you'd like me to avoid these things, I cannot. This is calculus-based physics. And it doesn't matter too much to us right now, but when we get into rotational motion, something that's very important to us is the rotational inertia, and that requires an integral over volume to understand. So it can't be avoided. Like, we do have to do volume integrals. And of course, you already have in Calculus 1, right? You did integrals of shells and things, but, so you have some idea of what a volume integral is, but not entirely, I guess. But anyway, we don't need to do all that. I think I just have one problem in your homework that's like this, which is why I wanted to do an example for you guys. So now that that's done, I have some time for questions. So if you guys got a question, you're welcome to ask. You guys have already figured out all the homework? It's all good? Okay. So anyway, anytime in physics we're doing something, we're setting up over a bunch of point masses, then there are three natural things to do. You can think about extending to like a one-dimensional object, or a two-dimensional object, or a three-dimensional object. Those respectively end up giving you like one-dimensional or two-dimensional or three-dimensional integrals in order to calculate the total mass in those different contexts. And so to properly set it up, you need to understand integration over areas, and integration over volumes. But there's a question. Go for it.
I have a question about one of the homework problems.
Go for it.
It was the one with the potential energy between two particles, and it's supposed to graph the potential energy versus the force. But we don't know what the constants are or which one is greater than the other. So I was wondering how you understand that.
Let's see here. Are you talking about 57? 58? Well, I suppose that we'd have to use algebra, right? So some of you are relying on graphing everything with a graphing calculator. So unless I give you numbers, you're up a creek, right? So that's unfortunate because you can't do this problem. But this problem can be done with algebra. So how would I graph something like that? I mean, fair enough question. I mean, there might be cases involved, I suppose. I did say A and B are positive, right?
Yes.
So we've got A over R to the 12th minus B over R to the 6th, right? So how would you graph that? U as a function of R. Like how do you go about doing that? I mean, clearly the graph is going to involve A and B, right? Let's see what else. I think the meaning of R here is that, I mean, I can simplify your life a little bit because R is a radius, right? So we're really only interested in looking at the graph for positive R, given the context of the problem. So we can assume R is positive. There, I have decreased your workload by 50%, right? You don't have to worry about negative R. I guess I can do this much algebra for you. And I think you can. I think you guys can all do this, right? Right? That reveals some things, I think. So it's definitely blowing up at 0, right? There's like a divergence there, I think. What else can I say? How do you figure out where it's 0? Right? How would you? What's an algebra thing we could do here? I'll tell you what. Let me do a similar but different problem. Suppose we had like A over R to the 8th minus B over R to the 4th. I'll make it a little bit different, but I can illustrate the principles involved here. Yeah. So I can factor out 1 over R to the 4th, and then I have A over R to the 4th minus B, right? If I was doing that problem, I do that. And then to make further progress, I would make a common denominator. There are various ways you could go here, but that's one way we could go. So 1 over R to the 4th, A minus B R to the 4th, yeah? Oh. Yeah, I just saw that, okay. I think we can do it, though. So this one, interesting. So wherever that's 0, that's where you'd have a 0 for this function. Let's see here. It might be easier. It's probably easier, actually. Let's not look a gift horse in the mouth here, so to speak. Really, the question is when is A over R to the 4th minus B equals to 0, right? So I was trying to attack this directly by making a common denominator here, and it's okay, but it's not really achieving my goal very quickly. I could factor that, right? But it's ugly to factor that. You know, you have a difference of squares. You got to think about. You're going to end up thinking about like 4th roots of A and things there. Now this is a little bit easier. See, if I just solve this equation, this tells me where I have 0 for U, right? And so we can solve that, right? So we have A over R to the 4th equals to B, which gives us R to the 4th is equal to B over A. I'm still assuming, as was in the problem, given that A and B are positive, right? So, yeah.
It's actually R to the 4th is A over B.
What have I done? Oh, yes, thank you. Muchas gracias. All right, let's see here. So, many thanks. Anyway, so then we take the 4th root. And because, thankfully, I told you R is positive, we've got 4th root of A over B. That's where there is a 0. the graph crosses the axis there, right? And so does it start out positive or negative? I don't know. I guess that depends on whether A or B is bigger, right? But for the sake of discussion, you can maybe say assume A is larger than B, right? So it starts out positive. There's two choices, right? Either A is larger than B or B is larger than A, right? It's one of the, or they're equal. If they're equal, then that's another case you could think about. But that said, for my hypothetical modification of your problem, it's something like this. It's got an intercept here at the fourth root of B over A over B rather. Thank you. That's where it crosses, and I know it does what? I know it blows up at the origin, right? So it's got a vertical asymptote over here. It goes through the origin, and what happens to it eventually? What's the limit as r goes to infinity for this? Zero, right? So that means it's got to do one of these kind of deals, right? It's got to come back to, it's got to have like a lowest point, and then it comes back, something like that. Now, how do you figure out where the potential well is? So this is, so far I'm just doing pre-calculus graphing, if you will, of U versus R. Now, to add some calculus to the mix, we should calculate what's du dr, right? So for my problem that's not your problem, but like your problem, we get minus 8a over r to the 9th, minus 4b over r to the 5th, I believe. Yeah? Because we add 1 to the power in the denominator when we differentiate. And then what? You'd solve where the derivative is 0. What would that tell you? That would tell you where there's a critical point for the potential energy. Yeah? So we set du dr equal to 0. In this case, it would be, if I set that equal to 0, I'd have, let's see here, 8a over r to the 9th equals to minus 4b over r to the 5th, if I didn't do it wrong. I think I did something wrong. Can you guys tell me? Yeah, I was about to say, there's no solution, no! But yeah, let's make that a plus. Thank you. And so with that adjustment, there's hope for solving this for positive r. Without that plus there, I'm in trouble. Anyway, so then let's see, so what I got r to the 4th equals to what? 8a over 4b. I'm too close to the algebra right now. Did I do it right? I think I did it. So that's what, 2a over b? So r is going to be the 4th root of 2 times a over b. So that's where the critical point is for the potential, right? In other words, in this sketch over here, this point is at r naught. That's where your potential well is, right? That must be something involved. That must be something about climbing. No, that wasn't something. Oh, you understand the physics. Oh, that's good. That's good. Woohoo! All right. So, so I said find the force as a function of one atom on the other. How do you find the force for part A? That means that's a deeply coded message to differentiate the potential energy function and multiply by -1, because the derivative of the potential energy is the force, right? Multiply by -1. F is minus du dr. Sketch the graph of both f of r and u of r. Now, I am not trying to graph f of r here also, but the graph of f would be minus this function. All right? And physically speaking, you should be able to kind of understand it. Remember how we talked about it? When the potential is decreasing, the force is pointing to the right, because the key idea in this case is F is minus du dr, because it's essentially a one-dimensional problem. So the gradient just becomes a derivative. And what that says is that when the potential energy is decreasing, then the force is pointing in the direction of positive radius, which would be to the right of my picture. If, on the other hand, the potential energy diagram was decreasing, increasing, then this would be negative. And so then the force would be pointing to the left. In other words, once I graph the force, it should be such that the force is positive to the left of R naught, and the force should be negative to the right of R naught, if I've drawn my picture correctly. Which would make sense if you think about motion that's bounded by that potential well, right? If you can imagine yourself being in here, you should be repulsed by the potential well as you hit it over here, and you should end up like bouncing back and forth like that. And so the scenario I just described, where we have the force pointing to the right if you're to the left of R naught, and the force pointing, I'm an idiot. Force pointing to the left if you're to the right of R naught, this way. And the force pointing to the right if you're over here, right, on that dividing line where the potential energy is 0. Because remember, the critical point for the potential energy is where what? Where du dr is equal to 0, which is to say that's where the force is 0. So the force is pointing to the left or to the right as you're on one side or the other of that critical line. Yeah.
So if the atoms were to start at like that positive potential energy to the left, would they just eventually like completely break away from each other because the other side of the potential well is not high enough?
Yeah, I think if your atom has more energy than this well, then it can disassociate. I think. What's that?
So if the potential energy of the particle is greater than
If you're exactly, and well, as we have it set up here, I think that would be the case. Like we don't have freedom to choose a 0 for the potential here because it was chosen for us by this formula, right? This formula has put the potential energy to be 0 at infinity. So if our energy level was like up here, for example, in my hypothetical, so your problem's up here, right? So these formulas are not for your problem. They're for a related but similar problem, right? And you're right, Simon. If we had that energy level for my problem, then that molecule would just so I suppose well, I mean, I'm kind of indicating to you that it's a stable equilibrium, aren't I? Yeah, if I say much more, I've answered part D, I think. Yeah? So pretty much I would have to have an energy diagram that was like down here to have bounded motion. Otherwise, what's the meaning of R? R is the distance of one of the molecules in the diatomic molecule from the other, right? So if that's not bounded, that means that eventually they just kind of rip apart, right? So, yeah. Whatever, I think essentially the dissociation energy is going to be whatever that energy is, however far your potential well is below the r-axis. Well, below the r-axis in my picture. But anyway, this is not a complete solution. Obviously, I also asked you to graph R. And so when you're asked to do a graph like this, you have to, be somewhat symbolic in your approach, and it's acceptable to make a reasonable assumption at the start, like suppose A is less than B for the sake of discussion, like I'm sympathetic to that. A complete solution, though, would have a picture for A less than B, A greater than B, and A equals to B, truth be told, right? I mean, that is what the analysis warrants. So, but some of you have a very bad habit of solving every algebra problem with the graphing calculator, which is, that's helped you out where you were. That's a lovely thing, but you need to be able to solve problems in closed form as well. That's part of this. So try to do that here. Other questions? I'm actually more scared of problem 59. Ugh, numbers. Those are like 10 to the minus 19th. Like, will my calculator go that far? I don't know. I'm just kidding. Any other questions? Yes, sir. Problem 60. Let's see here if I can just draw a picture. So we shoot an arrow at angle beta above the horizontal. So you've got a plane. So are you confused about the picture or just about how to go about solving it? Okay, so at least I've written the problem in such a way that it's not incoherent nonsense. So that's a start, right? Like that other problem about the halfway point. Aye, aye, aye. All right, so we're shooting it at an angle beta, right? Above the horizontal, and then the question is, what angle beta maximizes the range r? So I've defined the range to be like the horizontal distance covered, right? You could ask a different question. You could ask which angle maximizes the distance up the plane. That would be a different question, right? Maybe they're the same answer, I don't know. So what I would do here is I would use energy conservation to connect the two events, right? So what are the two events? You're firing it from here. It's going to here, right? So because we're not saddled with any preconceived notion of potential energy like in the previous problem, we can make the potential energy 0 on the plane, right? On the flat part. So we can say potential energy equals to 0 here. And so we have the energy at the start is equal to the energy at the end. And I believe what you're going to be looking at there is 1/2 mv naught squared, right? Equal to what? Is there kinetic energy up here? What's H equal to there? Maybe you guys can tell me that much. R what? R tangent alpha. Ooh. Sounds epic. Is that Lord of the Rings? No. Couldn't be that interesting.
Yeah.
Let's see here. Hey, wait a minute. Have you guys ever seen UHF? Maybe we should watch UHF one day. Let's see here. Let's see here. I want to believe, I'm tired. I believe you're right. So tangent should be opposite over adjacent. Yeah, we're right. It's good. All right, so then what? How about this? We've got 1/2 what? 1/2 mvf squared, right? And then what else? Plus mgh, which we apparently figured out is r tangent alpha. Now, what is vf squared, though? So keep in mind here that like v naught is a fixed given constant, right? For this problem. So that's something to keep in mind. How is vf related to v naught? You guys know? We have equations, right? Like we know that v naught is equal to what? As a vector, it's what? It's v naught, we got a beta there, don't we? So v naught cos beta, v naught sine beta. And VF squared is equal to what? It's VFX squared, right? Plus VFY squared. So now one of those I can figure out immediately. VFX squared is what? The acceleration in the x is what? Yes, v naught cosine beta, right? Because the acceleration in the x is 0, right? How about VFY? But we don't know time. We don't want to bring time into this. We got no time for that. Sorry, that was horrible. But it happened. I'm not walking away from it. I accept the accidental jokes that happened today. I accept them. My 11-year-old has, for some reason, gotten exposed to this video of Kenneth Copeland being confronted by a journalist, and he's shocked by how weird this guy is. He keeps talking about his eyes. He's got crazy eyes, and his hand was like doing this. Like, it's amazing. Yes.
Use the timeless equation and the vertical reaction.
Timeless equation. I like that. So what would that tell us? VFY squared equals what? V not y squared, right? Minus 2g delta y. Yeah. But putting that into, what is delta y here, though? We have another name for it. It's h, right? So, in fact, that's actually not h, it's what? R tangent alpha, because ultimately we're interested in the range.
But it goes up and comes back down, so the distance traveled is greater than h.
Oh, it doesn't matter. Because we're talking about that moment in time right here. So like the timeless equation doesn't care that it was higher at some other point in between. This is the delta y we're interested in. Delta y equal to h. So we can do that. And v naught y, well, we know this is what? Justin, you'll tell me. You got the other one. V naught what? This one, right? Sine beta. You got to square that thing. So, yeah. If I write much more, I will solve the problem. But like to tell you the path forward, what you want to do is we have figured out what the y velocity is at the end, right? So you take that and, I mean, here is the final speed squared, right? So you take what's in purple and you take this, right? Plug it in down here. See that? As usual for this problem, mass is irrelevant, so you cancel it off. It doesn't matter that you weren't given it, right? Cancel the mass. And look at what you're facing. You're facing an equation that involves what? It's got r, right? And is r squared? No, I think r appears linearly, right? You've got an r here, and you've also got an r up in here. But it's just sitting there, which means that you can take that equation and you can solve it for r, right? You can rewrite that as r equals to some function of beta. And then how do you maximize r with respect to your choice of angle? What do? You differentiate it, you set it equal to 0, and you solve that problem. Yep.
You also have to include the v cosine beta squared. Not just the...
Oh, yes. I'm sorry. That's VF squared. My bad. I should say this. This goes to here, rather. Thank you. And then this. No, curses. Thank you. So what I'm trying to say, but obviously I have not quite finished my connect the dotting. Well, anyway. All right, I think now I've finished my thought for all the equations which are on the board. Right, so you just need to put these together basically. And when you do that, then you can solve for r, and then you can maximize that by differentiating it and setting it equal to 0. And I think this one works out reasonably nicely. Like the algebra is not insurmountable. You can't do it with a graphing calculator. You'll have to do the algebra, but you can do it, I think. I have a solution somewhere, so. I hope that helps. We could have solved this problem before, but it would have been less fun, right? There's nothing stopping us from asking and answering this question at the start of the course. It's just we'd probably end up going through time and stuff like that, right? Unless we're just very careful to use the timeless equation, which is really to conserve energy, honestly. So, other questions? All right, well, let me talk about an example then. Well, I have just enough time to get into trouble. So let's talk about one of my favorite examples, the ballistic pendulum. So what's the ballistic pendulum? Let's see here. What is this, example 3? I don't know. So here's the deal. You've got this block, let's say with mass m, all right? And then this is like the block at a future time, all right? And so let me explain what happens here. You got this block sitting here, and this is it's a pendulum, all right? So it's free to swing about this mounting point. And then you've got a little bullet, mass little m, all right? And it's moving along here at velocity v naught, all right? What happens is that bullet, it shoots over, and it gets embedded. It sticks into this mass, all right? And then the bullet, the combined system, all right? So the m and the m, they swing up here, some angle, all right? And we're not really so much concerned about the angle. I'm interested in the question of how high does the system swing after it's been hit by the bullet? Like what's this distance here? If that makes sense. I can draw it more. Let me draw it more exaggeratedly so you can see it better. Let's suppose it swings all the way. Come on. Up here. So my bullet's embedded, right? How high does the pendulum swing? All right? You say that far? Sure, why not? So let me show you how I solved it. All right? Check this out. So I say, well, energy is conserved, right? So the initial kinetic energy of the bullet should be equal to the final kinetic energy. This is going to be the final potential. So this is like the max height, right? Top height, top of swing. So at the top of the swing, the kinetic energy is 0, right? So the energy is purely potential. So I was at 1/2 mv, 1/2. Why? What is that? Gah! Look at that. Behold, it's hideous. Yeah. 2. Whew. Man. Whew. Goodness gracious. Maybe today is not a day I should try to make corrections to your Calc 2 notes. M plus MGH. Right? And so then I solve for h. What did I get? I got h equals 2. Looks to me like, m v naught squared over 2g m plus m. You can check the units on it. It makes sense. It's like a kilogram meter squared per second squared divided by a kilogram times meters over second squared. It gives you a meter. So what do you guys think of this? I mean, when I did this in my first test in classical mechanics as a junior, I felt good about it. I felt like, yeah, I solved this problem. I solved it real good. And then I left the test and I started talking to my friend, Paul. I referred to him as Somber Paul. There were 2 Pauls I was friends with. One was the Crazy Paul. Still talk to Crazy Paul regularly. And Somber Paul, not as so much, but just lost his phone number. But Somber Paul went on to get a PhD in physics from UVA. And actually, Somber Paul is a formidable force in classical mechanics. And Somber Paul said, oh, yeah, that problem was easy. You just, I said, I just conserved energy. I solved it. And Paul's like, oh, yeah, I just conserved momentum, and then I conserved it. I'm like, what? You what? Oh, yeah, I conserved momentum, and then I conserved energy. And I was like, oh, I didn't conserve momentum. So, of course, this is wrong. But it looks right, doesn't it? Doesn't it? Why is this wrong? What's wrong about this? My initial phrase, energy is conserved, is false. Energy is not conserved in this process. This process of the bullet hitting the mass and embedding is by necessity an non-conservative process. It's an inelastic collision. Kinetic energy is lost in this process. Momentum has to be conserved, though. So momentum is conserved, which tells me if I just think about this just a second afterwards, right? Just a second afterwards, after the thing is together, it has velocity v1, right? So what I have is conservation of momentum. I have m times v naught is equal to m plus big M times v1. See, that I have to do. I have to conserve momentum in the process of the bullet embedding in the pendulum, all right? And that tells me the velocity at the start of the swing. At the start of the upswing, you got velocity mv naught over m plus m. And then what? Then I can conserve energy. See, once the collision's done, once the bullet's embedded, then I have a swing. I swing the pendulum up. That's a conservative process, assuming that, there's no kind of like friction in the joint of the pendulum or whatever. And so then I can go back and basically replace this. Then I have to do what? 1/2 m plus big M v1 squared. That's the initial energy of the system. And that's equal to big M plus little m gh. So my h is actually equal to v1 squared over 2g. The m plus m's cancel. And so the answer actually is this. 1 over 2g times m v naught over m plus little m plus big M squared. So there you go. That's the actual height that the ballistic pendulum swings up to. Now, I think in your homework, I might even had like a modification. There are various ways you can modify this problem and still make it an interesting physics problem. What are the things you could do? Instead of saying the bullet just gets embedded into the bob, the pendulum bob, right? You could, for example, you could let the bullet just, you could let it just shoot through, right? And I could let the bullet shoot through, and I could tell you the velocity before and after the bullet went through the bob, right? And then you could look at the fact that energy momentum was conserved, and it would tell you how much momentum was transferred to the pendulum bob in that way. Like that's another modification. You could let the bullet shoot through, So anyway, any questions about this? Yeah.
Is energy's not conserved because of the deformation of materials, right?
Yes. So next time, and I was going to do that this time, but you know what? We had questions about homework, which is great. So next time I'll talk about elastic versus inelastic collisions and And we'll talk about elastic collisions in one dimensions have particularly special formulas. There's some really neat things that happen there. But yes, by definition, an elastic collision is one for which the kinetic energy is conserved. And those are precious and rare in terms of the world of all collisions. So anyway, that's all for today, folks. So.